Thank you very much for that nice introduction. I appreciate it. Can everyone hear me okay?
Yes.
Very good. It's wonderful to be in Dresden, beautiful city. I love it. This is my first time in Europe, believe it or not. So it's a great experience for me. The other great experience is I get the opportunity to talk to you all about devices, which I find very exciting, and to try and explain how we think they might work. I'm not saying we know for sure, but how we think they might work, and perhaps start getting some good dialogue on these devices. We like to call this new device, it's a Memristor, we call it the self-directed channel. And this is a name we came up with just recently to differentiate it from some of the other Memristors, which could be confused with this one. It's an ion conducting device. We're going to talk about electrical properties, some materials variations, as well as what happens when you put copper in the system instead of silver. And then we're going to do a live demonstration. We've got Tim Moulter from Knowm who's going to come up and actually connect a good demo board, and we'll show you a Memristor in action with a few of Professor Chua's experiments shown. So the basics of the SDC Memristor first, it's bidirectional, so it's bipolar essentially. Voltage controlled, resistance variable. I call it non-volatile, but I want to talk about that a little bit. Generic Memristor, I'm not differentiating it any more than calling it generic. It's not extended. And this type of device uses a chalcogenide glass and a source of easily oxidizable metal, like silver or copper. And because we typically use a germanium selenide with silver in a layered structure, it leads to confusion with CD-RAM, which often uses a germanium selenide in glass. But the devices are completely different. And I'll go through that so you can understand more what I mean by that. The basic structure, this is the most basic device that we've initially studied, researched to try and understand how it worked and modified from there. It looks complicated. It consists of an active layer, germanium selenide, Ge2Se3, and that's important, followed by a metal selenide layer, typically tin selenide. And then we've got this germanium selenide mix layer, a layer of silver, germanium selenide adhesion layer, and a tungsten layer. This layer here, the Ge2Se3 active layer, germanium selenide active layer, next to this tungsten bottom electrode. This active layer is the most important layer in the stack. Everything else looks very complicated, but it's not. These three layers, they're basically put together as the silver source layer to prevent silver from migrating through and poisoning the cell. And it also allows tungsten to deposit nicely over the system, otherwise it won't. So it's really a fabrication issue, it's not complicated. And the other easy thing about this is you can put all of these layers down in one step in a fabrication tool, a sputter tool. So even the top electrode, it's all done at once. It's simple, no photo doping, it's very easy and very fast. And we can do it at a university fabrication lab like Boise State's, getting undergrads to do the fabrication on devices, and we always have more than 95% yield. It's a really good, simple process.